Chapter 10, Organohalides. In the first section, we are going to learn the naming and the synthesis of organohalides. Halogen elements include fluorine, chlorine, bromine, iodine. An organohalide is an organic compound containing at least one carbon-halogen bond. Organohalide has many uses, including fire-resistant solvent, refrigerants, pharmaceuticals, and precursors. Naming of alkyl follows the same rules for naming alkenes. A halogen is treated the same as an alkyl substituent, but is named as a halo group. For example, this is called chloro, and this is called bromo. So first find the longest chain and name it as a parent chain. So for the following two examples, okay, both molecules, the longest chain have 7 carbon. So they both called heptane. All right. Then you number from and nearest any substituents. So for the first molecule, we number from the left to right, 1, 2, 3, 4, 5, 6. So the first substituent is bromo, which is number 2. Now if you go from right to left, then the first one will be a methyl group on the number 3. So 1, 2, and 3. And therefore, from left to right, give you the smallest number for the first substituents. All right, so that's the correct numbering. And the molecule should be called 2-bromo. Okay, bromine is number 2, and you have 2 methyl. Okay, one is number 4, one is number 5. So 4,5 dimethyl heptane. Okay, 2-bromo 4,5 dimethyl heptane. Note that we use hyphen, okay, in between these numbers. All right, and the next molecule. We also number from left to right, so the methyl group would be the first substituents. If you go from right to left, again, the first substituent will be number 3, which is not correct. It's not the smallest number. So the correct numbering is from left to right. So in this case, you have number 2, number 4 methyl, so 2,4 dimethyl. And the bromine is number 5, 5-bromo. Okay, but when you number it, naming it, you should follow the alphabetical order. So bromine is in front of methyl, and therefore you should put 5-bromo, okay, 2,4 dimethyl heptane. If in a molecule the halide and the alkyl group are equal distant from the end of the chain. For example, if you number from left to right, methyl is number 2. If you number from right to left, the bromine is number 2. So both are equal distant from the two ends. In this case, okay, we follow the alphabetical order. So bromine is in front of methyl, and therefore we number from left to right. And therefore, this is called 2-bromo 5-methyl hexane. And if you go to the left to right, 5-bromo 2-methyl hexane is not the correct naming. In this slide, we go over some of the common alkyl groups that you learned in Organic 1, but you are also going to see this in this chapter. So when you have an alkane, but one of the hydrogen is replaced by atom or a functional group, it becomes a substituent or a group. For example, propane, you have 3 carbon, but if the hydrogen is replaced by a functional group, okay, for example, the first carbon has a hydrogen replaced by hydroxy, so this is called a substituent or group called propyl. All right, so this molecule is called propyl alcohol or propane propanol, all right, propyl alcohol. Now, if the second carbon loses a hydrogen replaced by hydroxy, okay, then this is also propyl, but called isopropyl. It's an isomer, so it's isopropyl. Now this structure can be redrawn like this. All right, so again, it's a second carbon. All right, one hydrogen is replaced by hydroxy, and so it's isopropyl alcohol. But this drawing is more common. All right, so called isopropyl group. Now, if we have 4 carbon, okay, butane, all right, so one of the hydrogen is replaced by a functional group, then there are many possibilities. So, for example, this is one possibility. It's called butyl or N-butyl because it's a linear. Okay. Another possibility is like this one. If you count, it's still 4 carbon. So 1, 2, 3, 4. Still 4 carbon. So it's still butyl. All right. Now, but the arrangements are different. So this is called iso. Okay. It's an isomer, so it's called isobutyl. Okay, so note that isobutyl, isopropyl, they have similar structure. They all have a tail, CH3, CH3, and then one have a CH2, and that's called 4 carbon, so isobutyl. And this has 3 carbon, this has 4 carbon. So imagine if you have 5 carbon, but the same tail. So note that CH3, CH3, CH3. Okay, same tail, but you have more carbon. So this is 4, that's the isobutyl. But if you add one more, then that's have 5. So this is called the isopentyl. All right, so note the tail, the same tail. That's called the iso. So isopropyl, isobutyl, isopentyl. So for 4 carbon, you have more arrangement possibilities. So this is another one. Okay, note that this metal is not here. That's the difference. And this is called secondary. So secondary butyl. Secondary means the carbon that attached to functional group. For example, here is a hydroxy. This carbon attached to 2 carbon. So 1 carbon, 2 carbon, and that's called secondary. On the other hand, the last one, this carbon that attached to a functional group have 3 carbon, 1, 2, 3, and this kind of group is called tertiary butyl. Okay, so tertiary means a carbon that attached to 3 carbon. Okay, so this tertiary butyl can attach to, again, alcohol. That's called tertiary butyl alcohol. Okay. Covalent bonds are formed by 2 atoms sharing 2 electrons. For example, hydrogen molecule have 2 hydrogen atoms equally sharing 2 electrons. Sometimes electrons are not equally shared. For example, when hydrogen and chlorine form a bond, the 2 electrons are more drawn towards chlorine because chlorine is more electron negative, so it likes to pull electron away from hydrogen. And because hydrogen has less electron density, it's partially positive. And the chlorine has more electron density, it's partially negative. And this bond is called a polar bond. All right, it's a polarized bond. Now, similarly, when carbon and halogen forms bond, the bond is polarized with slightly positive charge on carbon, slightly negative charge on halogen. Here is a quantum mechanical calculation of a alkyl halide. So this is a methyl group. The center is the black one is carbon, so it's a CH3, and this is chlorine. So the calculation show chlorine has more electron density, so it's partially negative. We use red color, Okay, the red color indicates it has a high electron density. It's a partially negative charge. On the other hand, the carbon has less electron density. It's partially positive, and we use blue color to indicate the positive charge. Here's another drawing. Okay, so the bond, carbon halogen bond, is polarized with halogen atom partially negative, carbon atom partially positive. Now this polar bonds has important consequence on the reactivity. Later we'll show you that alkyl halides undergo nucleophilic substitution reaction. And if you have a negative charge atom or group such as hydroxy, it's a negative charge, it will attack the positive charged carbon instead of chlorine or fluorine, which is a negative charge. And when it attacks carbon, it forms a new bond, okay, carbon-oxygen bond. At the same time, the bond between carbon and halogen will break. So in effect, it forms a new bond to replace an old bond. And so that's called nucleophilic substitution reaction. In the following, we are going to learn how to prepare alkyl halides. Here's the alkyl halides, and this alkyl halide can be synthesized from alkene undergo radical halogenation reaction, or it can synthesize from alkene with a double bond by electrophilic addition or NBS allylic bromination. And the third method is to make alkyl halides from alcohol undergo nucleophilic substitution reaction. The reagent we are going to use either HCl or thionyl chloride. We're going to see details next. Let's first discuss the preparation of alkyl halides from alkanes. Now, alkanes such as methane contain only carbon, hydrogen. There's no functional group, so alkanes are usually very stable. The only reaction they involve are combustion reaction or radical reactions. Now, radicals are the species that contains unpaired electron. For example, chlorine has 7 electrons. So when you draw Lewis dot structure, there is 1 electron that is unpaired, and this is called a radical. Radicals are extremely reactive. So in nature, chlorine does not exist as a chlorine atom because it's a radical. Instead, it forms 2 radicals combined together forms a molecule. So that's a chlorine molecule. Okay. So for a radical reaction, usually you need a radical initiator, so you can generate a radical, or you add UV light. Okay, this means UV light. This will break the chlorine molecule into 2 radicals, and the net effect, the overall reaction, is methane plus a chlorine, and one of the hydrogen is replaced by chlorine, forms methyl chloride with hydrogen chloride. Radical halogenation reaction usually involves 3 steps: the initiation step, propagation step, termination step. In the initiation step, UV light is used to break the chlorine-chlorine bonds, forms chlorine radicals. So in this step, the radical is generated. Now remember, radicals are very reactive, and so it immediately attack anything else. So in the system, you have methane in it. So the next step is chlorine radical. Okay, you have 1 electron. It wants to pair electron. Now note that carbon hydrogen has bonds. Each bond has 2 electrons. So radical needs 1 electron. So it attack the electron with hydrogen. So forms hydrogen chloride, but then 2 electron becomes 1 electron. So you generate a new radical, and this is called the methyl radical. Okay, so methane becomes methyl radical. Chlorine radical forms hydrogen chloride. Now remember, radicals are reactive, so this methyl radical will not stop here, but react with anything else. So in the system, you have chlorine molecule. So the next step is the new methyl radical attack chlorine. So chlorine bonds, again, you have 2 electrons. So the radical combined with one of the electron forms methyl chloride. At the same time, it generates a chloride radical again. So note that these 2 steps, the first step forms hydrogen chloride, which is one of the product, but also generate a new radical, methyl radical. And then methyl radical attack chlorine molecule forms another product, methyl chloride, but also at the same time generate a new radical chloride. And then the chloride radical repeat the first step. Okay, attack methane forms methyl radical, and then methyl radical attack chlorine forms methyl chloride and chloride radical. So in the propagation step, one radical reacts with a reactant to form a product and also form another radical. Okay, another radical repeats its step, okay, again and again. So that's the propagation step. Now at the certain point, there are enough radicals are generated. These radicals may combine. So chloride radical, when they combine, they lose the unpaired electron because they pair each other, forms chlorine molecule, or methyl radical, or chlorine and methyl radical share the 2 electrons. They lose the unpaired electron. These are termination steps. As we just shown in the last few slides, under UV light, methane, chlorine undergo radical halogenation reaction, and the product is one of the hydrogen is replaced by chlorine. However, radicals are extremely reactive, and therefore radical halogenation is usually hard to control. The reaction not stop at this stage. Instead, second hydrogen may be replaced, third hydrogen may be replaced, or even 4 hydrogens are all replaced by chlorine. So the product is usually a mixture of all these alkyl halides. Now, if the synthesis goal is to make one of these alkyl halides, then radical halogenation is not the best choice for synthesis. In this slide, we go over the terminology of primary, secondary, and tertiary carbon. The name depends on the number of carbons directly attached to the carbon you are interested. For example, if this carbon is the one you are interested, because this attached directly to one carbon, okay, with other 3 hydrogens, and this red carbon is called primary carbon. Now, if this is the one you are interested, because this is attached to 2 carbons, 1, 2, and this is called the secondary carbon. And this carbon directly attached to 3 carbon, and therefore this is a tertiary carbon. And this one attached to 4 carbons directly, so it's called a quaternary carbon. Now this terminology is very useful. For example, if this is the one you are interested, because this carbon has a positive charge, it's called a carbon cation. And because this carbon attached to 2 carbons directly, 1 and 2, and so this is a secondary carbon cation. This carbon has a unpaired electron, so it's a radical. And because this carbon attached to 3 carbon, 1, 2, 3, and therefore it's a tertiary radical. And this carbon attached to a bromine, so it's an alkyl halide. And because this carbon attached to 1 carbon, so it's a primary alkyl halide. This slide shows the relative reactivity of a carbon-hydrogen bond to form a radical. R represents alkyl group. Think about CH3. So this is a primary carbon because it's attached to 1 alkyl group. This is a secondary, you have 2 alkyl group, and this is a tertiary. The experiments show that tertiary carbon is the most reactive to form a radical. So when this carbon-hydrogen bond break, this forms a tertiary radical. All right, so tertiary carbon is the most reactive to form a radical, followed by secondary carbon, and the primary carbon is the least reactive to form a primary radical. This relative reactivity has been attributed to the stability of the radicals. Tertiary radical is the most stable radical, followed by the secondary, and then primary. Now imagine the waterfall. Okay, so water here, and you have two locations. One is A, one is B. Now B is the lowest location, so it's the most stable location. A is higher, okay? So eventually water all goes to B, okay? Because B is the most stable location. So water goes B instead of A. So the most stable location is the place where water goes. Similarly, the most stable radical, tertiary radical, is the most easy to form. So tertiary carbon is the most reactive to form tertiary radical, followed by the secondary carbon. And because the primary carbon is the least stable, and therefore is the most difficult to form. So why is this relative stability of these radicals? Radicals are electron deficient. Usually electrons are paired. Here radical only have one electron. So that's why radicals are not stable. They are very reactive. But in tertiary carbon, you have carbon bonds. This carbon-carbon bond has electrons that can donate to this radical to make electron more density, increase electron density, and therefore stabilize the radicals. Okay, because you have three of them, all right, so you make it more stable. On the other hand, secondary carbon, you only have two carbon-carbon bonds, and the primary you only have one, and so least possible to donate electron to make it more stable. So tertiary is the most stable radical, and tertiary carbon is the most reactive to form the radical. Let's look at the radical halogenation reaction. Suppose only one hydrogen is replaced by chlorine, and this hydrogen may be here, this one, and that will give you the first product, okay? Or the hydrogen may be here, this hydrogen, and that will give you the second product. All right, now the hydrogen may be this one, but that gives you the same product. And same is here, this hydrogen. So the second product, you have 9 hydrogens that can be replaced. The first product is formed by replace only one hydrogen. So statistically, the ratio you get should be 1 to 9, because you only have 1 for the first product, 9 for the second product. But it turns out that the first product is formed by a tertiary carbon. This carbon is a tertiary, and therefore we learned in the last slide, tertiary carbon is the most reactive, okay, because it forms a most stable radical and then forms the product, add the chlorine. All right, so reactivity to form the first product is the most reactive. So instead of forming 1 to 9 ratio, experimenters show it's 35 to 65. It's about 1 to 2 instead of 1 to 9. Okay, and this is because of tertiary carbon is more reactive than primary carbon. Okay, so imagine this carbon, tertiary carbon, has the hydrogen same number as the primary. Then you would expect the ratio will be much higher, maybe 9 to 1. Right? If the tertiary carbon hydrogen is the same number as the primary. So far, we have discussed the formation of alkyl halides from alkane through a radical halogenation reaction. Now, let's discuss the second method, the preparation of alkyl halides from alkene. In Organic 1, you learned that alkenes undergo electrophilic addition reactions. Alkenes contain double bonds. A double bond is electron-rich. When hydrogen chloride is added to the solution, because hydrogen and the chlorine bond is a polar bond, hydrogen is partially positive and the chlorine is partially negative. The electron-rich pi bond will flow to the hydrogen atom to form a bond, carbon-hydrogen bond. At the same time, the other carbon becomes a carbon cation, which connects to the chlorine to form a carbon-chlorine bond. So the net effect is hydrogen adds to one carbon, chlorine adds to another carbon to form an alkyl halide. The reaction also follows Markov-Nikov rule, and that is the hydrogen adds to the carbon that already have the most hydrogen in the original molecule. And that's why here the product hydrogen adds to the right side carbon, and the chlorine adds to the carbon that has the fewer hydrogen in the molecule. Now, the double bond may also react with the bromine molecule to form a dibromide. In this slide, we show the mechanism of electrophilic addition. Drawing mechanism is very important in learning organic chemistry. In Organic 1, you already learned some simple mechanisms, so how to draw mechanisms. Now, if you are not familiar with this, if you forget about it, I suggest you to follow the steps and draw it as many times as you can until you are confident that you can draw these mechanisms. So electrophilic addition reaction involves two steps. Okay, here step 1, step 2. In step 1, first you draw an arrow to show the electron flow from the electron-rich pi bond. Okay, you have a double bond, so pi bond has 2 electrons here. The arrow shows these 2 electrons flow towards the positive charged proton to form a carbon-hydrogen bond. Now, because hydrogen can only form one bond, and therefore you draw a second arrow to show hydrogen-chlorine bond break, so that only hydrogen attached to carbon, but the chlorine gains an electron. The 2 electrons both goes to chlorine, so instead of 7, now becomes 8 electron. It's a negative charged chloride. Now, because the 2 electrons here, pi bond, move to form a carbon-hydrogen bond, this carbon lose a electron, so you should draw a carbon cation. And therefore, after the first step, you form a carbon cation with a new carbon-hydrogen bond, okay, and also a chloride anion. Now, because carbon cation is positive and the chloride is negative, so the second step, you draw an arrow to show the lone pair electron of this chloride move towards the carbon cation to form a new bond, carbon-chlorine bond. And that ends the mechanism to form alkyl halides. Also notice that, again, you should place the hydrogen, added hydrogen to the carbon that has the most hydrogen in the molecule. And that's called the Markov-Nikov rule. Now, again, I suggest that if you are not familiar, you must repeat many times so that you can draw this mechanism. Similarly, for the reaction of bromine you join also two steps. In the first step, the two electrons pi bond move, draw the arrow towards the bromine to form a carbon bromine bond, and another bromine leave to form a bromide. Now in this case, instead of forming carbon cation, the bromine, because the size is big, so it actually, instead of connect to one carbon, it actually connect to two carbon, so to form a bridged bromonium ion. So the next step, the second step, the bromide, which is negative charged, attack one of this carbon on the back, because bromine is big, block the face here, so it has to attack on the other side. So the product is a dibromide, but it's anti-addition. Our textbook also show the preparation of alkyl halide from alkene through allylic bromination using NBS. In this class, we are going to skip that section and go directly to the third method, preparation alkyl halides from alcohol. When hydrogen chloride or bromide is added to a tertiary alcohol, the hydroxide will be replaced by a halogen to form alkyl halide. This reaction is most effective for tertiary alcohol. Now in the next chapter, we are going to learn the mechanism of this type of reaction, and we show the reaction undergo SN1 reaction. For SN1 reaction, tertiary is the most reactive, followed by secondary, primary, and methyl alcohol. And therefore, this reaction to form alkyl halide using hydrogen chloride bromide most effective for tertiary alcohol. Now, if it's primary alcohol, the SN1 reaction becomes so insignificant that the mechanism changes to SN2. And for SN2, we need a stronger reagent such as thionyl chloride and phosphotribromide. And we're going to see more in the next slide. Here shows some examples of preparation of alkyl halides from alcohols. So in this alcohol, the carbon is tertiary, so it's a tertiary alcohol. Adding hydrogen chloride will replace hydroxy by chlorine, forms a tertiary alkyl halide. In this reaction, ether is a solvent to dissolve the reactants. Now, here shows two alcohols, both are secondary. Okay, so for secondary alcohol, SN1 reaction becomes very slow. Particularly for primary, we need a reagent such as SOCl2, called thionyl chloride. Now, thionyl chloride provides chlorine so that it can replace hydroxy to form secondary or primary alkyl halides. And the reaction will undergo SN2 reaction, so we are going to see the mechanism in the future. In this reaction, we add the pyridine as a base to neutralize the hydrogen chloride formed in the product. Similarly, if we want to replace hydroxy by bromine, we add phosphorus tribromide, which provides bromine to replace hydroxy. Again, in this reaction, ether is used as a solvent. In the last slide, we showed that alkyl halides can be synthesized from alcohols. But how do you make these alcohols? In Organic 1, we learned that alcohols can be made by hydration of double bond. Hydration means add water. So water is H2O, HOH. By hydration, OH adds to one side carbon, hydrogen adds to another carbon, and that gives you an alcohol. Now, hydration of alkene have three ways. Okay, so number one, the reaction is called hydroboration oxidation. In hydroboration oxidation, you have two steps. One, you add diborane, diborane B2H6, or you can write BH3. Okay, BH3 is called borane. If two of them combine together, that's diborane. So that's the first step. You add borane or diborane. And then followed by the second step is hydrogen peroxide, and under basic condition. If you combine these two together, the two steps together, then water will be added to double bond, and the reaction also follows anti-Markov-Nikov rule. And that means the hydrogen adds to the carbon that has the least hydrogen. Remember, Markov-Nikov rule says hydrogen adds to the carbon that already has the most hydrogen. But the anti-Markov-Nikov says the hydrogen goes to this carbon that has the least hydrogen. And hydroxy adds to the carbon that has most hydrogen, which has one hydrogen in this molecule. Okay, so hydroboration, oxidation give you alcohol, follows anti-Markov addition. Also note that you added the hydroxy and the hydrogen, they are on the same side. It's called the syn addition. Okay, so that's the method 1, hydroboration, oxidation. Now method 2 is called oxymercuration, demercuration. So you also combine two steps. Step 1, you add mercury acetate. So this is acetate, mercury acetate in water THF solution. That's the first step. Followed by second step, sodium boron hydride. If you combine these two steps, then water will be added to the double bond, and it also obeys Markov-Nikov rule. Okay, method 1 is anti-Markov-Nikov. Here is Markov-Nikov. So the hydrogen goes to the carbon that already have the most hydrogen. Hydroxy goes to the carbon has the fewest hydrogen. All right, so that's the second method. Remember, combination of mercury acetate, water in THF. Second step, sodium boron hydride. When you combine these two together, you get an alcohol, follows Markov-Nikov rule. But if you use borane followed by hydrogen peroxide, whenever you combine these two together, then water will add to double bond to form an anti-Markov-Nikov alcohol and a syn addition. The third method is simply add acidic condition, add water. So you add hydrogen chloride with water, then it will give you water will be added, and alcohol will be formed, and also it's a Markov-Nikov addition. So these two are similar. However, this method, simply adding hydrogen chloride, acid condition in water, is not preferred because the reaction has many problems. So the best way to make Markov-Nikov product, alcohol, is to use oxymercuration, demercuration method. Okay, so again, these materials you already learned in Organic 1. If you are not familiar, all right, you should go over this material. These are important materials. In summary, alkyl halides can be prepared using several methods. In method 1, it is formed from alkanes. The reaction involves radical halogenation. Okay, the reaction mechanism has 3 steps. The reaction is difficult to control and usually involves a mixture of the product. Alkyl halide can also be synthesized from double bond. The reaction is electrophilic addition. When hydrogen chloride is added, hydrogen will add to the carbon that has the most hydrogen, and the chlorine adds to the carbon has the least fewest hydrogen, and this is called the Markov-Nikov rule that gives you this major product. And this is a minor. Okay, again, textbook also have NBS, allylic reaction, but we skip that step reaction. Okay. Alkyl halide can also synthesize from alcohols. These undergo nucleophilic addition. If it's tertiary, we simply add hydrogen chloride. The chlorine will replace hydroxy, forms tertiary alkyl halides. If it's secondary and primary, then you need a reagent as thionyl chloride, which provide chlorine. Now, if you use thionyl chloride, pyridine has to be added to quench the hydrogen chloride that is formed in the product. If you want to replace hydroxy by bromine, then phosphorus tribromide needs to be added. After watching this video, you should read the textbook. Combine this video with textbook and work on the problems in the textbook. Problems 10 to 1, 2, 3, 4, and 8. You may skip 5, 6, 7. The textbook has answer keys to all these questions. If you have time, also work on additional problems in the textbook. Remember, learning organic chemistry requires lots of practice. All right. In the end, we'll have exams, we'll have questions similar to these problems. So it's important that you can do those questions. Now, if you have a question, please ask. All right. We can set up an appointment. We can talk online using Zoom or Blackboard Archer.